Today we're going to be talking about section 1.7, linear independence. So in the last video, we talked about homogeneous systems. So systems of vectors where they equaled the zero vector. Now it turns out if you have a homogeneous system of equations, you always have a solution. You have the trivial solution. So that's the solution where all of your variables equal zero. And if you have more than the trivial solution, if you have a non-trivial solution, then you have infinitely many solutions. If you only have the trivial solution, there's a special name for that. Those set of vectors are called linearly independent. So a set of vectors is linearly independent if when we take their vector equation, set it equal to zero, when we take that homogeneous system, we only have the trivial solution. So these weights, these variables, x's right here, all have to equal zero. In contrast, they're called linearly dependent if there exists some weights that aren't all zero, so that when we take that linear combination and set it equal to zero, this system holds. So again, remember that if we have a non-trivial solution, which is what we're really saying right here, we're saying the system has a non-trivial solution. If we have a non-trivial solution, that happens if and only if there is a free variable in this system. So if we're trying to tell whether there is, whether a set of vectors is linearly independent or linearly dependent, we just need to check to see whether there's a free variable. Let's take a look at what that might look like. So let's say we want to know our three vectors, let's call them v1, which is the vector 1, 2, 3, v2, the vector 4, 5, 6, and v3, the vector 2, 1, 0. We want to know, are these linearly independent? So what is that actually asking? What that's actually asking is, in this system of equations, if we set this as a homogeneous system, is there only the trivial solution, or is there a free variable that will give us a non-trivial solution? Well, the only thing we know how to do so far is put vectors into an augmented matrix and row reduce, and it turns out that's exactly what we want to do with this. So we want to know, okay, in this homogeneous system, what kind of solution set do we have? So let's go ahead and stick our vectors into our matrix and augment it with the zero column because we're looking at homogeneous systems right now. And row reduce. So if we row reduce, we end up getting our reduced row echelon form as 1, 0, negative 2, 0, 1, 1, 0, and 0, 0, 0, 0. So right off the bat, you see that because we have this zero row, we do have a free variable, so the system is linearly dependent. So that means that we can write the system as C1 V1 plus C2 V2 plus C3 V3, where our C's are not all zero. This is what it means to be linearly dependent. So what are those weights then, if they're not zero? Well, there are infinitely many of them, but we can come up with an example of what those weights might be by putting the solution into parametric vector form like we did in the last video on section 1.5. So our solution set, again, we have three variables. So this will be x1, x2, and x3. And if we want to put this into parametric vector form, we take a look at that first row and we say, okay, x1 is going to equal to 2x3, x2 equals minus x3, and x3 equals itself because it's free. And we can factor the x3 out to give our final solution as x3 times 2, negative 1, 1. That means that any value of x3 will work. So for instance, if we let x3 equal to 1, then we can have our weights be 2 minus 1, 1. So we can write this set of vectors as 2 times v1 minus v2 plus v3 equals 0. So again, we have weights that aren't all 0 that makes this homogeneous system work. So these vectors are linearly dependent. So we can easily tell whether or not a set of vectors are linearly independent or linearly dependent by putting our vectors into an augmented matrix and row reducing. But we might like to develop some shortcuts so we don't have to do that every single time, because row reducing can get a little tedious, as I'm sure you've gathered so far. So let's talk about a couple of shortcuts that we can use to identify quickly whether a set of vectors is linearly dependent or linearly independent. If we have two vectors, this is actually quite easy. So if we have only two vectors, then two vectors are going to be linearly dependent if and only if they're scalar multiples of each other. This is actually pretty quick to see, because if two vectors are linearly dependent, that means we can write them as CV1 plus DV2 equals 0, and C and D are not going to both be 0. So without loss of generality, let's just assume that C is not 0. Then we can solve for V1 by moving dv2 over and multiplying or dividing that by c. And we're allowed to divide by c because c is not 0. So look at that. v2 is a multiple, a scalar multiple of v1. In contrast, if they weren't linearly dependent, so if c and d had to be 0, we wouldn't be able to divide by c because c would be 0 and you can't divide by 0. Okay, so if you have two vectors and they're scalar multiples of each other, you don't have to put anything into a matrix. You can right off the bat tell that they're linearly dependent. We can do a similar thing if we have a set of more than two vectors. It's not quite as obvious right off the bat, but if you have multiple vectors, then they're going to be linearly dependent if and only if at least one of the vectors is a linear combination of the others. So we can figure this out basically exactly the same way as we figured out with two vectors. So if we have a set of vectors that are linearly dependent, then we can write them as C1v1 plus C2v2 and so on, plus CKvk equals 0, and not all of those C's are 0. So without loss of generality, let's assume that C1 isn't 0. This is what it means to be linearly dependent. And again, we can solve for V1. So we can go ahead and subtract off each of the other terms from 0 and then divide everything through by C1. And again, we can do this because sorry, writing and talking at the same time is hard. We can do this because C1 isn't 0, so we can divide by C1 with no problems. So we see that we can write V1 as a weighted sum of the other V's. And so what does that mean? Sorry, this should be V2. What does that mean? That means V1 is a linear combination of the other V's. So again, if we have a set of vectors that are linearly dependent, then at least one of them must be a linear combination of the others, and vice versa. Another way of saying this is that V1 is going to live in the span of the rest of those vectors, V2 through Vk. So our set of vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the other, if and only if at least one is in the span of the others. Okay. So that's another shortcut. So if you have a set of vectors and one of them is in the span of the rest of the vectors, you're linearly dependent. We have a couple of more shortcuts that we can do. One shortcut that is really easy to see is that if you have a set of vectors, let's say we have a set of p vectors, and they live in a vector space with smaller dimension than that, so these vectors are going to live in Rn, then those vectors have to be linearly dependent. So again, if there are more vectors than the dimension that they live in, they're dependent. This is pretty easy to see. Let's say we have 3 two-dimensional vectors. So let's say our 3 vectors are 1, 2, 3, 4, 5, 6. And, sorry. And again, we're looking at this in a homogeneous equation. If we look at this, there are at most 2 pivot positions. But there are 3 variables. That means automatically we have to have a free variable. It's impossible not to. So these are automatically linearly dependent. We have more vectors than the dimension of our space. We're linearly dependent. One last one I want to show you guys, which again is going to be really easy to check, is if we have our set of vectors. And again, let's have these vectors live in Rn, although in this case it doesn't actually matter. So we have our set v1 through vp living in Rn. If any one of those is the 0 vector, then it's automatically linearly dependent. And again, this is pretty easy to see why. So let's say, for instance, that v1 is going to be the 0 vector. It doesn't have to be your first vector, but let's just say it is. Then we can easily write 1 times v1, that's still going to be 0 because any scalar multiple of 0 is still 0. And then the rest of our weights can be 0 for the rest of the vectors. This is obviously going to equal to 0 because 0 times anything is 0, and v1 is the 0 vector, so this will be 0 also. So here we have a homogeneous system, and we have a non-trivial solution because this 1 right here is not 0. So these are linearly dependent. So to recap, a system is linearly dependent if it has a non-trivial solution, if it has a free variable. It's independent if the homogeneous system only has the trivial solution. This is just a rephrasing of what we were doing in the last video, where we were taking a look at homogeneous systems and finding their solution sets. And we can shortcut finding whether or not a system is dependent. If there are only 2 vectors and they're scalar multiples of each other, they're dependent. If one of the vectors is a linear combination of the others, they're linearly dependent. If you have more vectors than the dimension of your space, linearly dependent. And if any of your vectors are the 0 vector, automatically linearly dependent. You don't have to check anything. You don't have to do reduced row echelon form. That is all I have for you today. I will see you all in class.